Hi, guys. We'll just give it a minute for other people to arrive. How you guys doing today?
Doing well.
Good.
Just got my first COVID vaccine, so I'm excited about that.
Good for you. Excellent. Is Northeastern doing that on campus then?
No, I'm actually back home in New York right now. I just got it from New York State.
Okay. Okay, good. All right, while we're waiting for others to show up, let's talk about administrative stuff, about like what's coming up, because there's a lot of stuff happening. All right, so today, so notably today we have a quiz. This is on chapter 3.5. We're just going to be focusing on the disk method. Okay, so this is like the stuff that we did earlier. I guess it would be about a week ago now that we did that. So that's the focus for our quiz today. Okay, so keep that in mind. We also have homework for chapter 3.5 due, and this is for the whole thing. Okay, even though our quiz is only covering disk method, chapter 3.5, the whole thing will be on the exam next week, so keep that in mind. So make sure that you're clear on like how to do stuff like that. So also today, our topics, what we're going to be covering is chapter 3.9. Okay, so make sure you've got like your lecture examples ready to go for that, because we're going to be covering that out. So we ended up having to drop chapter 3.7 because we couldn't fit it in the time frame when we lost the class period yesterday. And then also it looks like this semester other sections were not covering 3.8 and 3.4. If we get a chance at the end, like if we have time to do it, then I'll cover these. Okay, I'll post like lecture examples and stuff, and I'll post what the homework assignments would be, although they're not due, they won't count for anything, and they won't be on the final. But it may be of interest to you, and it may be helpful to kind of think about what the topics are. Basically mass and density, and variable density, centers of mass, things like that. And this is areas swept out using polar coordinates. So these things can all help you in other classes that you're talking about. And so chapter 3.9 is essentially the last chapter section that we're talking about for chapter 3, okay, for what will be required to know for the final exam, for our exam or whatever. Okay, so let's talk about next week. Actually, tomorrow, you guys should start taking a look at the Canvas page for the next week's module. I haven't posted it yet, but I will probably tomorrow. Next week's module, I'm going to have review materials. So these are like old midterm exams that you guys can take a look at. We covered maybe different things, but mostly it was the same. So on that other exam, these old exams, you'll see things from like 3.7, 3.8, which won't be on our exam. So I'm just going to keep that in mind. But there'll be old things here. The things that I think are going to be most helpful to you to study for the exam are going to be things like our old quizzes, right? And then the homework problems, and then certainly the examples from the lecture examples. Okay, so these are sort of like, in decreasing order, like what will help you. Okay, so you can take a look for that. It'll be in next week's module. Okay, so like next week is where we're going to post the midterm exam. Okay, so let's talk about what's going to happen. So next Thursday, so in a week from today, next Thursday, we have our midterm 2. And this covers chapters 3. So this is like 3.1, 3.3, 3.5, and 3.9 now. So chapter 3 and chapter 5, okay? And then also don't forget 4.5 and 4.6. This is our interval of convergence. So remember how we did that before, the radius of convergence, and then we actually had to find the exact interval, okay? So now, given all the stuff that we learned in chapter 5, we'll know how to do this interval of convergence. Okay, so that's something that you want to make sure that you have in mind. So that's next Thursday, and then the homework due for this will be chapter 3.9 will be due next Thursday. Okay, so kind of keep that in mind. Some of you guys have asked me about homework solutions. Homework solutions are going to get, I won't post them until next week, probably Wednesday. And then the reason I do that is because some other sections of Calc 2 actually have people pass in their homework for grade. Like they, when they take a look at the homework, they actually grade it for correctness, which we don't do, right? I mean, I just take it and I look at it for completion, but not for correctness. And so I can't post the solutions to it until I know that the other sections basically have covered it all. Is it 3.1 or 2.1 on the left? What do you mean? Right here, that's a 3. So chapter 3, which includes 3.1, 3.3, 3.5, 3.9. So that's next Thursday. So then what's going to happen next week is, in terms of topics, Monday, we're actually going to start chapter 1 of the multivariable book. So this is the Calc 3 book. Okay, so make sure that you have a copy of that. You're going to need it next year, next semester when you take Calc 3. Okay, even if you're not taking Calc 3, see if you can't get a copy of it, because in there's going to be a lot of detailed information about stuff. So we're going to go through chapter 1.1 pretty quickly. It has a bunch of like terminology and things on it to think about, but no homework for this one. And then chapter 1.2 is where we're really going to pick up. So no homework. And then homework. The thing is, for this, I have to actually type in the homework for chapter 1 multivariable, and I haven't done that yet. So that's on my list of things to do. I'll probably get to that tomorrow. I'll start posting homework, but you'll see that we're going to start that on Monday. Okay, so then that homework will be due after our exam. So I wouldn't even really worry about, excuse me, worry about this until like doing the homework until after our exam. Okay, so Monday we're going to start the multivariable book, 1.1 mostly, 1.2, and then Wednesday is a review day. So this is review for the midterm. So come on Wednesday prepared to ask questions. You can ask questions on the old exams. You can ask questions on homeworks and quizzes and stuff like that. Yep, that's my next thing. So what's going to happen on Thursday, right, is that on Thursday, so the exam is a timed exam, right? So the exam will open during class time. So if you want to, you can take the exam during our regular class time, okay? It'll open during the class time. This is the availability. Okay, the availability window opens in the class time, and it'll be open for 24 hours. But it's a timed exam, so the minute that you start it, you have to finish it. Okay, you'll have 65 minutes to take it plus 15 minutes for text stuff, just like last time. Okay, only this time I'm only going to do one question. I think I was trying to do like 4 questions, thinking it would be if you couldn't do multiple PDFs or whatever. But I'm just going to do one question this time. So make sure you have one PDF or JPEG of your exam allowed. So make sure you consolidate everything, and make sure if you do it in a JPEG, make sure it's not so far zoomed out that I can't read it. It's going to be worthless to me like that. A PDF would be great. So that means on Thursday, there's no class, right? No class period, no class meeting or meeting. Okay, because we have the exam, it'll open up during that time frame. So our exam will run from 1:35 on Thursday to 1:35 on Friday, which means you should start it no later than noon at Eastern Standard Time, so that you have plenty of time to take pictures and upload those pictures to Canvas. Okay, make sure that that's there. All right, you guys, I think that's about all I needed to cover in terms of administrative stuff. But I mean, obviously I'll have office hours, so I'll have office hours on that Thursday. So you're free to come earlier that day, because I'll have office hours before your class. Okay. Questions about all that? It's a lot of stuff coming up. We're actually coming up right in the end of the semester. There's a lot of things kind of happening all at once here. So think about that. Okay. So the midterm exam is just the stuff that we've been covering since our first midterm exam. Okay. This stuff here. And then our final exam will be cumulative for the whole semester. So keep that in mind. There's a lot of stuff on the final. Okay. think that's about it. All right, you guys. So let's go ahead and get started on chapter 3.9. So chapter 3.9 is called Work and Energy. There's you can expect to see a work problem on the midterm exam and on the final exam. There's always one on the final exam. We're going to go through our lecture examples has an old final exam question on it because it's really it's kind of a common question that you want to be able to think about. So we've got two different types of work that we're going to talk about. Actually, work, the same type of work, but two different types of forces. One is a constant force, one's a variable force. So the first one, work done by a constant force. We'll talk about that briefly. It's pretty straightforward. So work itself is done by a force when it moves an object. Okay, so we think about work. If an object is moved a distance, we'll call it d, in the direction of the force. So I've got an object and it's being acted upon by something, and so it's going to push that object. So the force is happening, it's pushing that object a certain distance in the direction of the applied force, F. Then the work, W, done is given by this. So work equals force times distance. W equals F times D. We're going to talk about this, you know, force times distance and all that. Well, we're going to kind of revisit it very briefly again in the multivariable area. This gets, you know, easily done when we're talking about vectors and stuff. We'll do that in the multivariable. All right, so let's talk about the forces that we could be thinking of, right? So we've got gravitational. We have electromagnetic. We have strong nuclear and weak nuclear. So our force is a push or a pull. You guys, probably you've seen a lot of this stuff in your physics classes, but I need to give you the background on it so that when we actually get to the math, the nitty-gritty math problems, we're all kind of on the same page. The gravitational forces on Earth, typically our unit of measure for that is the weight, right? So if we're dealing with weight, then it's basically we've already multiplied the mass times gravity, okay? So if we're dealing in something, if it's given to you in pounds, which is I think slugs maybe is the is another metric for weight, but it's but when we deal with another metric for force, but when we deal with weight, okay, then we're talking about mass times gravity already. So be very careful. Look at your units when you're given a problem, okay, because often if you're given it in terms of pounds, LBS, pounds, right, then we've already taken into account gravity. So don't multiply it because it'll you'll just be double counting it. All right. All right, so I've got my lecture examples here. I'm gonna start pulling things out. Okay. Okay, so example number 1, determine the work done by lifting a 50-pound object 4 feet. So I'm just gonna, I've got my 50-pound object. You know, here's my 50 pounds. And I want to take it and I want to lift it 4 feet from here to here. Okay, so the work done is force times distance, right? Our pounds, that takes into account the mass times gravity. So this is the forces, right? We're basically looking at, 50 pounds. And we're going to go a distance of 4 feet. And this is in foot-pounds as our unit of measure. Okay. Not so bad. Incidentally, when we talk about a Newton, which is a measure of force, our units for that, remember, is meters per second squared per kilogram. Okay, so acceleration per kilogram, right? That's our force unit. Our work, right, is force, so it's newtons times meter. So Newton meters is also called a joule. Okay, just, you've probably seen this already in physics, but you can get something called a dyne is a centimeter gram second. Okay, so just kind of different metrics for how we want to categorize this stuff. Okay, so constant force, was the example that we just did. Okay, our second type of force is the one that we're really going to be focusing on, which is work done by a variable force. So you have to have a more complex way of looking at it because the force is going to vary as a function of like distance, right? And so, or a function of position. So we have to think about how we're going to set that up. Okay. So our amount of force changes as the object, oops, I can spell object, changes position. Okay, so you can think about it as an object moving along a straight line from x equals a to x equals b by a continuously varying force. Capital F of x. Now remember when we first did our integrals, we said we're going to integrate f of x to get capital F of x. This is now our force. So be careful. This is our force as a function of position. Okay. All right. So instead of just giving you the equation or the formula, let's talk about like where it comes from. Okay. So I'm going from A to B, right? And I'm going to be moving some object along that path. And I want to calculate the work it's going to take to go from A to B. Okay, now what I need to do is I need to think about, because my force isn't constant, so I can't just go force times distance, right? My force is going to be changing. So I'm going to look at, I've got this, interval from A to B. I'm going to divide that up into sub-intervals, tiny little slices, and calculate the force, calculate the work, and then sum up all of those work values from A to B. So this is the process that we're going to be thinking about. Okay, so I'm going to say my delta x is a partition that divides A to B into subintervals. Okay, my delta W sub I, this is my work, is my F, my force, right? So I've got my force at this particular position times my distance, that tiny little sliver. How far? That delta x, we just went this infinitesimally short distance, right? What was the work within that? So let's say our C sub I is our position within our A to B interval, okay? And we're at the ith interval, right? So I is going to start at A, it's going to increment by some value, and it's going to go all the way up to B, right? So our total work, we want to sum up all of these delta W's, right? So my total work W is going to equal to, I'm going to sum up I equals 1 to N. I'm going to sum up all of these delta sub I's, W sub I's, which is I equals 1 to N. I'm going to delta X sub I. Okay, now you can imagine n is the number of subintervals, right? So like we've always done, where if I increase the number of subintervals to a lot, I'm going to get a really good value, really good approximation of what's happening. If I can increase the number of subintervals to an infinite number of subintervals between A and B, and I'm going to make them infinitely thin, I'm going to get like a pretty exact copy of what's happening. So that means that I'm looking at the limit as n goes to infinity. So, oops, you can't see it. As n goes to infinity. So the number of subintervals from A to B, right? So if I increase that to like an infinite number, right? And I calculate, whoops, C sub I delta X sub I, right? I calculate out all of those work values, right? I've got an infinite, this thing is infinitely thin, right? This is like basically, I'm going to sum them all up. Well, I can't sum them all up. Oops, I forgot my summation. I equals 1 to n. I'm going to sum them all up. Well, an infinite sum is the way of saying I'm going to integrate from A to B. So this is my work. I'm going to integrate f of x dx. Okay, so this is our formula right here. But basically what it means is we're looking at kind of like the idea that we did at the very beginning of a constant force, right? You know, so constant force times the distance. So the distance that we're moving is this infinitely thin piece. And what was that force that was applied in that infinitely thin slice? And I'm just going to add up that next one and the next one and the next one and the next one, right? Adding up an infinite number is like, I'm just going to take the integral. That's integrals of summation. Because this is what we're trying to do here. Okay. So we talk about different kinds of forces. We're gonna, I'm gonna give you 3 different examples of different kinds of forces, okay? And then we'll go through some other examples. These are things that you'll need for your, like your homework, but also in general, we're mostly talking about gravity when we do example questions on stuff. But in terms of your homework things, you're gonna need to know stuff like a mass spring system requires Hooke's law. So this is a force required to compress or stretch a spring within its elastic limits right? We're not going to stretch it so far out that we're actually stretching the metal. We're just saying the spring can go out this far or it can be compressed this far. So within its elastic limits is proportional, right? This is proportional. It looks like alpha, but it's kind of like a proportional to the distance d. The spring is compressed or stretched. And we need a proportionality constant, K. Okay, so we're looking at our force is equal to minus K times D. Okay, this is Hooke's law. K is our proportionality constant. D is the distance that we're stretching or compressing. So you can think about, we'll just draw a couple different pictures here briefly. So I've got a wall. I've got my mass. It's attached to the spring, so it's right at equilibrium. Right, it's neither stretched nor compressed, it's just resting. It's not moving at all. Right, I've got my, this is my horizontal. You can imagine, here's my 0. Here's my mass. Right, it's being compressed. Okay, if it's being compressed, right, I'm pushing it this way, but the spring is pushing back this way. So this is the spring force, right? So as we push it, the spring is wanting to push back. You can do the same thing where if I stretch it, so here's my equilibrium, here's my mass, try to over exaggerate that it's being stretched, right? So we've taken this mass and we've pulled it out from its equilibrium position, and the spring wants to go back. So that's the direction of our spring force. These are just different visualizations of the direction, right, of our spring force. Okay. Okay, so that's a spring, Hooke's law. Newton's law of universal gravitation is our second type. Okay, so let's write out what this is. So the force, this is again a force description, the force of attraction. So these are all the different, these are like some of the different types of forces that we would use to do force times distance, right? So the force of attraction between two particles, and we're not talking about gravity and these things here, but except for this universal gravitation, but this is like attraction between two particles of masses m1 and m2, m1 and m2, is proportional to the product of the masses and inversely proportional to distance squared. Okay. All right. This is the distance. D is distance between the two masses or two particles. Okay. So this force is given by, we're going to write out with this G m1 m2 all over d squared. So m1 and m2 are typically in kilograms. D is in meters. Our force then is in newtons. Okay. G is our universal gravitational constant. I'll give it to you in a minute. You don't expect you to have this memorized, but so this is meters cubed per kilogram second squared. Okay, that's what this force describes here. Okay. I think you need these for your homework. And we'll do a mass spring example before we then move on to gravity stuff. Okay, so our third type of force that we'll give you, Coulomb's law. You see this in like electrical circuits, right? Coulomb's law is the force between charges, Q1 and Q2, in a vacuum. And this is proportional to the product of the charges and inversely proportional to the distance squared between the two. The distances between the two charges. Right, so let's talk about, we write down Coulomb's law. Force is K, a proportionality constant, Q1, Q2, d squared. K you might be given, K might be 1. If you're not told, you can assume that it's equal to 1. Q1 and Q2 are in electrostatic units. And then D is typically in centimeters. If it is, if D is in centimeters, then we're talking about this is in dynes. Okay. This is just things that you'll need to answer the homework, and then, would help you in other stuff. Okay. So example 2 is a mass spring system. We'll do that example. Okay. And then we'll do a couple examples with gravity, because the gravity problems where we have to move something and it's been affected by gravity, then those are typical types of problems that you'll want to be thinking about. Okay. So example 2, a force of 750 pounds compresses a spring 3 inches from its natural length. Find the work done in compressing the spring an additional 3 inches. So we have 2 parts to this problem. The first part is going to help us calculate our proportionality constant K. Okay, so I'm going to set this up. Force equals K times D. So that's 750 equals K times 3. Okay, and now, you know, if K is negative and we're compressing, we're going like this is going to be a negative force. So K is going to always be positive. Okay, so I'm going to go K equals 250. That's my proportionality constant. Okay, so now let's just kind of think about what we're doing. So I've got this. This is on my x direction. This is 0. This is 15. So this is how it is normally. Okay. First part, right? We're going to compress it. We're going to take this and we're going to compress it 3 inches. So here's 0. Right. So here's our, so we're going 3 inches compression, and this whole thing here is 15. Right. So this is, oops, let me write it here. Compressed 3 inches. This is what we just work with in order to figure out what our K is. So now we're going to go another 3 inches. So here's my first 3, here's my next 3, and now I really compress this spring. Right, so this is 3, there's a 0, there's another 3, right? So now, and here's after compressed, another 3 inches. The another is really important, okay? Because we've done the first 3 that helped us figure out what K is, and now we're going to do another 3, okay? So really what we're doing is we're going from, this is from 0 to 3, and this is from 3 to 6. So we're really looking at what's happening, what's the work being done here, right? Because we already calculated, we already know the work here, okay? Or we can calculate it. Anyway, so let's do this. So to find the work, my delta W equals force times distance. So my force is K times X times delta X, right? So this is my force and this is my distance, right? That tiny little sliver that we're going. We're going to sum this up, right? So my total work, remember we're going from 3 to 6, right? And I'm going to go 250x times, well, sorry, dx, okay, dx now because I'm summing them up in an integral. They're really infinitely thin, which is, this is just the power rule. So this is 250 divided by 2, x squared, evaluated from 3 to 6. Often I can tell you in a lot of these problems, we tell you just to set up the integral, because usually evaluating the integral is trivial. Okay, so, but we're going to keep working it through so you can see it. This is in inch pounds. If you wanted this to be in foot pounds, you can just convert this, you know, our inches, we can convert that into feet if we wanted to. So I just want to write down a note to take note of. Do not integrate from 0 to 6, okay? Because we used that 0 to 3. We were given that information. We were told a force applied, going from 0 to 3. That's what we did to calculate K. It's already compressed when the clock starts ticking when we're looking at the work. We're going to compress it from 3 to 6 now using that proportionality constant. Do not integrate from 0 to 6 because you were asked to find work in compressing the spring an additional 3 inches. Okay, so keep that in mind. It's very, very important on these examples to read all of the details, like the doubles and the details on a lot of these examples. Okay. All right, so let's start taking a look at gravity. So these are typical of the types of problems that you would see on like a test or a final or something. So Often we're dealing with some kind of a geometric shape. So look, we have a tank, it's spherical, and it has a radius of 8 feet, okay? It's half full of oil, and the oil weighs 50 pounds per cubic foot, right? So this isn't exactly force, this is like, you know, it's like a force per unit of, you know, density, right? Cubic feet. So we want to find the work required to pump the oil through a hole in the top of the tank. So there's a lot of words here and no pictures. So nobody grades your pictures, but the pictures are going to help your brain kind of calm down and think about where all these numbers go, and then help you think about like what you need to do. So the first thing I'm going to do is I'm going to draw a sphere. Right, so I've got this sphere here. Remember, we always judge the radius at the equator here. So the radius is 8, okay? Which also means I've gone 8 here, and I'm gonna go another 8 there. So this tank is 16 units high. So what I'm gonna do, watch what I'm gonna do. I'm gonna start thinking about this in terms of an X and a Y axis, just because I'm gonna be integrating, right? So now what we're going to do is we're going to put a little, we've got a hose. We're going to do this hose, and then the hose is going to siphon that oil out. Okay, so I've got to be able to move the oil, right, from here up to the top, from here up to the top, from here up to the top. So this is what we're trying to do. We're trying to get this oil out of the tank. It's a spherical tank, right? But now let's think about what we have. So our tank is 16 units tall, okay? And I've got this cross section. My cross section is a circle. Okay, and it's got a little thickness. We'll call this our thickness here. We're moving up. We're going to go from y equals 0 to y equals something. So we're operating along the dy axis, right? So my thickness here is, it's going to be infinitely thin, right? We're going to take this tiny little sliver. It's a circle. We're going to lift that circle up and out of the tank. So this is how we're thinking about our work, right? Okay, so I'm going to subdivide this thing into all these tiny little circles. Now, I drew it here for a reason, because it's half full, right? So it's half full, 8 feet, half full, right? That's why I drew that sort of, you know, my water line or this oil line right here, half full, okay? The fact that it's half full and it has a radius of 8 feet have nothing to do with each other. We could have said it's full up to 15 feet, say, for example, and then you just have, we would draw our line up here, but our radius is always measured at the equator. Okay, so let's start thinking about what's going to happen. So we've got right here. So our increment of force, right, is given by weight for each disk. Okay, so we're looking at in each disk is a circle with area pi r squared and thickness delta y, which becomes dy when we go to integrate it. Okay, so my delta F is my weight, which, remember, we have 50 pounds per cubic foot, and then we have times the volume, right? Because I need to, this is a cubic foot. So I want my force in just 50-pound units, right? So I got to think about, what am I going to do here? So I've got 50 times pi r squared delta y. So my volume of this circle, right, is the area times the thickness, okay? So this is the area of the circle times the thickness of the circle, okay? And this is in pounds, delta F, okay? So my R, I have to think about my R, okay? So my R, this is in my X direction. So my R is really 50 pi x squared delta y. Well, but I'm looking at delta y and x squared. And I want this all to be in one variable, right? Because I'm going to be integrating. I'm going to go dy, right? I'm going to integrate with respect to y because I'm moving things up. Okay, so that means I need to convert this x squared or solve it in terms of y. All right, so let's take a step back and think, right? Our shape is a circle. So our equation for a circle goes like this. X minus h squared plus y minus k squared equals r squared, where h and k are the center. Okay. So let's think about where's our center here. My center is right there. Right? So the center of our whole sphere, center for our very centered circle is gonna be, let's see, I've gone 0 in the x direction, and I've gone up 8 in the y direction. Okay, that's the center. So I'm gonna write out my equation here. So x minus 0 is x squared plus y minus 8 quantity squared equals, my radius is 8 squared. So that's 64. So if I solve this in terms of x squared equals 64 minus y minus 8 quantity squared, I'm going to FOIL this out and combine it with 64. Okay, so I'm going to get x squared equals 16y minus y squared. I encourage you to go ahead and prove that to yourself. FOIL this out, combine it, you'll see you're going to get this. Okay, so now this x squared is what I'm going to plug into this x squared. Okay, we're going to plug that in there. So now everything's going to be in terms of y. Okay, that'll be very convenient. So let's do that right here. So our delta force is equal to 50 pi x squared dy, which is equal to, now we can substitute for the x squared. So 50 pi 16y minus y squared delta y. That's our delta force. Okay. All right, so that's our first part to think about. Our second part, we had to calculate the delta F. We had to do the radius. So let's do this. Delta F. We need to do our radius. In L3, we have to go, what's our height? Okay. Okay, so the height, let's go back to our drawing and think about it. Okay, so my total height here is 16, right? We were told has a radius of 8 feet, which means our total height is 16. We filled it up halfway, but that doesn't matter. This one here, this circle, we know the very top sliver is at 8 feet. But what if I go like a nanometer down? Oh, geez, I'm at, 8 feet minus a nanometer, right? Or if I go like a couple, if I'm like here, where am I? So, right, so not only is my radius going to be changing with where I'm at in the height, which is what we were calculating here, because our radius changes with respect to our height. Basically, right, the distance that I need to move this sliver up is different than the distance that I need to move this sliver up. It's all based on where we're at in the height. So this thing here, or even the ones that are down lower, are going to be at a height of y. I don't know what that is. It's whatever y is, right? That's kind of like, where is my position? It's y. So the distance that I need to move that is my total distance minus how far I've already gone. So my height is going to be 16 minus y. That's how far we need to move that distance. So this is our distance to move. Okay. Why don't let me just write that as distance, not height. Height makes it sound like it's kind of a misnomer. So distance. Okay, and I'll call this here, instead of height, I'll call it distance. So this is the distance that we're moving that sliver of oil up. So the distance is going to be 16 minus y. Okay, so I'm trying to really, step you through all the whole thought process of how we're actually making this work. All right, so let's do our integral. Work equals A to B force times distance, right? So let's set this up. Work equals, since our tank is half full, right? Which means we were going from 0 to 8 feet of oil. Okay, that tells us how much we need to integrate across. Think about it like this. We go back to our drawing, right? I'm going from 0 to 8 feet. That 0 to 8 feet is the half full. If it was full up to 15, I go from 0 to 15 because I'm taking all those little slivers from 0 to 8, right? And I'm going to sum them all up. That's what we're doing. So that's always, this is how much oil we're lifting up. So from 0 to 8, okay? Now I'm going to start putting everything together. I've got 50 pi r squared dy, and then times the distance that we're going to go. So I'm going to go 50, comes up from here, right? 50 pi 16y minus y squared. And I'll put the dy at the end because we're going to go 16 minus y dy. Normally on exams, you're asked just to set it up, but not to integrate. So I'll put a circle around this, but we're going to go through and do it so you can see, because we want to do like a quick check to see, is this like in the right ballpark or not? Okay, so I'm going to, this would be your answer. But let's go ahead and integrate it so we can get a number, and then we'll just do a reality check on that. So I'm going to FOIL all of this out. This is an 8. I'm going to FOIL all of this out, 50 pi. And this is, once I multiply everything out, I'm going to get 256y, 32y squared, y cubed, dy. You can see why we don't even really ask you to integrate it, because it's just trivial with the power rule. So this is going to be 50 pi. 28 y squared minus 32 over 3 y cubed, fourth y to the fourth, and we're going to go from 0 to 8, and we're going to get I got 50 pi times 11,264 all over 3, which was approximately 82 foot-pounds of work to lift that up. We're just going to do a quick back of the envelope check to see if that makes sense. Like, is that reasonable? I'll let you guys finish writing that. Okay, so let's do this. So I'm going to put a little continued, quick check. You don't have to do the check. This is just for us to see. Are we thinking about, did we go too far out, or is this okay? So is this work reasonable? Is the answer reasonable? So let's think about it like this. So the weight of the oil in the tank, and the tank is half full, right? So this is, it's a half full tank. So we have half the volume times the density. Okay, so a volume of a sphere, 4/3 pi r cubed, right? So 1/2, because it's half full, 4/3 pi 8 cubed times our density is 50 pounds per cubic feet. It's going to give us on the order of 53,616.5 pounds. So this is our force, right? And now if we're going to lift the entire sphere up 8 feet, right? So imagine, like, instead we said, let's take each sliver of oil out and then calculate the work. Now imagine we have it in the tank, we have a sphere, I'm just going to lift the sphere up, right? So what's the work to do that? That's going to be work is equal to force times distance. So this is, we're pretending this is just a reasonable back of the envelope. Our force, 53,616.5 times the distance of 8 feet. It's going to give us 428,932 foot-pounds. So it's the same ballpark, right? The other one was on the order of 500,000. Now we're on the order of 400,000. They're different, right? Because this is a constant force. The other one was more accurate. but it's the same ballpark, right? They're the same order of magnitude. If I got here like in the millions or in the 10,000s, like if they were off by an order of magnitude, I think, oh, I did something wrong. Okay, so same order of magnitude, so same ballpark. So I can feel reasonably confident that my answer on the previous page is reasonable. It's just like one of those mental checks. Is this in the right ballpark? Okay. All right. Next question. I threw this in here because it's from a final exam. So it's good to think about. This is a common one. Everybody likes this geometry here. It's a right circular cone with a vertex at the bottom. You wouldn't have a tank like this, but we like it because it's weird geometry. And it requires you to think in terms of similar triangles. So you have a cone with the vertex at the bottom, like here's the ground. Sometimes they do this, it's embedded in the ground and you have to, you know, whatever. So it has a radius of 8 feet at the top. And it has a height, a total height of 17 feet. Okay, the tank contains water up to a height of 13 feet. So we're like here, 13, right? So we're going to go from 0 to 13, right? That's our bounds of integration. The rest is empty. The water density, right, is 62.4 pounds per cubic foot. So we have our force per volume here. So what's the work required to pump all the water up out of the top of the tank? So let's remember our work equals the integral of force times distance. Okay, so again, I've got circles as my cross-sectional area. So our area pi r squared, but my radius changes as I go, right? So the radius is big at the top and it's smaller as I go down. So I have to find a way to relate the radius, which is really our x, right, to our position in y, because depending on where I'm at, my radius is changing, right? So I'm going to set up a proportion. I'm going to say when I'm at the top, my radius is 8, and then my y position is 17. They gave me the total height. I'm going to solve for x, cross multiply, divide. So I'm going to get 8y over 17, right? Gives me my radius in terms of my position along the vertical. Okay, this is the x that I'm going to put in here, x squared. So now when I put that in there, I'm going to go pi r squared times our height, right? How far up are we going to go? D. Okay, so this is the distance that we need to travel. So again, like we did before, our distance, this total distance is 17, right? But I'm not lifting, I'm lifting this piece 17, but I'm not lifting that piece 17. So it's going to depend, my distance, I should have done it elsewhere. My distance is going to be 17 minus where we're at in space. This is our distance, right? So pi r squared times distance, so pi r squared 8y over 17 squared times our distance, 17 minus y. Okay, so that gives us where we're at. This here comes from our similar triangles, by the way. Okay, so if I set up a triangle here and I set up a triangle there, I can think about, you know, finding out what's that proportionality between the similar triangles. So my work, now we said it was filled from up to 13 feet, so that gives us that. So I'm going to put in my density of the water. So this is 62.4. Don't forget this bit. That tells you how much does your water weigh. You have to take that into account. So the water has a density, okay, which is in terms of, it's in pounds. So we've already taken into account the force of gravity. So that whole thing there, times pi r squared 8y over 17 squared. Right here, times our distance that we're traveling, times the dy. This is the thin sliver. That's how thick each circle is. It has this cross-sectional area here. Okay, so now normally we just tell you to leave it. Like once you set up the integral, you can set it up but do not evaluate. But sometimes we tell you to evaluate it too. So let's go ahead and keep working it through. So I'll start multiplying through all of the numbers. So I'm going to square 8 and square 17. I'm going to leave y obviously it's a variable squared. So, and I'm going to multiply it by 62.4.6 divided by 289, and this is times pi 0 to 13. What do I have left? I've got y squared, 17 minus y dy, which I can distribute this, right? So this is going to give me 17y squared minus y cubed dy. And then I'm going to integrate using the power rule. This is why we don't worry about it, because the hard part is setting it up. Okay, so this becomes 3993.6, 289 pi. Y cubed minus 1/4 y to the 4th, and we're going to evaluate from 0 to 13. And then I got that was equal to 73,369.06 pi, or I can multiply through 230, 495.72 joules. Okay, but like I said, often we tell you just to set it up and then leave it. Okay. I'll let you guys finish writing that, and then we're going to talk about energy, kinetic energy. Okay. Okay, so kinetic energy mostly. Energy, so we talk about a variable force, F, and it acts on a particle with mass, M, over a given, oops, GIV, given distance along a straight line. You'll learn about things in space when you do these calculations with vectors. Okay, right now we're just focusing on straight line. Let's think about it as the x-axis. So the force does work, but also imparts acceleration. Okay, so remember, acceleration is the derivative of velocity with respect to time, to the particle. So our Newton's laws, second law of motion says F equals ma, but I'm going to convert a to dv dt, and v, remember, is the derivative of our position with respect to time. Distance is how far a force would have to pump the oil water from the same elevation to the top of the tank. So you want to go back to here. So this question here, Harrison, you're asking about the distance, right? So you can imagine I've got this sliver, right? It's at position Y, and I have to move that, right? I have to move that 17 minus Y. That's the distance that that sliver is traveling. That's going to travel. The next sliver is at a different Y, and it has a different radius, right? There's a different Y, and that needs to go 17, my total minus whatever that is. That's our total distance. So Y is how far up we've already gone, right? And then 17 minus Y is the total distance that that particular piece needs to go. Does that help? We're not going 17, because not every sliver that we're working with is at 17. Like the very most bottom one is at 17. That's when Y is equal to 0. Okay, but the one that's here is not going 17. It's going 17 minus 13. It's only going 4 feet, right? So that's why we have, but we don't know. I mean, all these slivers are infinitely thin, so we have to take into account all those continuous positions along that Y. Okay, it's kind of, that's why I take so long to draw these out and to think these out, because you really want to kind of picture what's actually happening. Okay, so let's go back to our energy here. So m dv dt, but v is dx dt, right? So this is the second derivative of position. Okay, so our acceleration produced by a force changes, I'm trying to speed up, changes the velocity v of our mass m, and therefore changes its kinetic energy. Okay, this is the kinetic energy, is the energy due to motion. Okay, so our kinetic energy, oops, is equal to 1/2 mv squared. Okay, but this comes from, we're going to actually just do the integral right now. So if the particle starts at rest, the work is our kinetic energy. And it goes like this. My work, I'm going to integrate from a to b, my force times dx, a to b, mv dv dx, right, times dx. So this becomes a to b mv dv, which gives us our work is equal to, right, we're going to integrate with respect to v, so 1/2 mv squared evaluated from a to b, which is 1/2 mv b squared minus 1/2 mva squared. This is our kinetic energy. And there's a last example to actually calculate this, but I think I'm running out of time. So what I'm going to do is I'll put that into, there's an example, example 5, which does the change in kinetic energy. And so I'll put that in on the lecture examples, and then I'll scan it all in so you guys can take a look at that last example. Okay. Phew, there's a lot of stuff, right? So that's the end of chapter 3. So keep in mind the quiz that opens up today is 3.5 disk method, so 3.5 part 1, right? The stuff we did a week ago. And then the test next week will cover all the chapters of 3 that we covered, 3.1, 3.3, 3.5, and 3.9. If we have a chance, we'll come back to other chapters, sections of 3 at the end of the semester, just so you guys can have the information. If it doesn't work, then we can't. I don't know, for paper. I know. I hear you. I'm going through a lot of paper too. Yeah, excellent. Well, that's good. You'll have a good resource to to study from and to have this for next semesters too. Okay. All right, you guys, listen, have a great weekend. I will see you on Monday. Take a look at the multivariable book. Don't forget our quiz is going to open up in 20 minutes. Okay, it'll be open for 24 hours. Okay. Have a great weekend, guys. Take it easy.
Thank you.
Bye.